Hi all! This is the last video of the 22nd chapter on FreeRTOS from the Crystal Clear Electronics 2 curriculum. In this video, we will learn about the notification and queue features.
Both features are intended to provide communication between tasks. We will first get acquainted with the notification feature. Basically, it's a 32-bit variable that allows us to send messages between threads. Each time a task is created, a notification object is created for the task, which beside the 32-bit value also has a state. This can be waiting to be processed, pending, or has already been processed, not pending. Each task can wait for its own notification, or you can notify tasks from other tasks or from the interrupt handler. Using notifications requires much less runtime and memory usage than using other synchronization objects such as semaphores.
To send a notification, the xtaskNotify or xtaskNotify from ISR functions can be used. The xtaskNotify has three parameters.
The first one is the xTaskToNotify, the handle variable of the task to which we want to send the notification. The UL value is a 32-bit number. This will influence the value of the task's notification variable. The last one, the eAction, will define what should happen to the UL value. In the case of eNoAction, the task receives the notification, but the notification variable is not changed. This way, the second parameter has no relevance. This is useful if we only want to wake the task, but we don't want to provide further information. When using the eSetBits, the notification variable of the task is bitwise ORed with UL value. This can be useful if we assign some meaning to each bit of the notification variable. This way we can set them. In the case of eIncrement, we increase the notification variable of the task with 1. This way, the UL value has no relevance. Using the eSetValue with overwrite, we copy the UL value to the task's notification variable. In the case of eSetValue without overwrite, UL value is used to override the notification variable of the task only if there is no unprocessed notification. Otherwise, the function will return with an error and the notification will fail.
We can wait for the notification of our task with the xtaskNotifyWait function. This has four parameters. The UL bits to clear on entry is a 32-bit number. It specifies which bits to clear when we start processing this notification as the first step of the xtaskNotifyWait function. For example, 0 means none and 0xFF means the lower 8 bits. The UL bits to clear on exit is also a 32-bit number. It specifies which bits to clear on exit as the last step of the xtaskNotifyWait function. The pull notification value is a pointer which points to a 32-bit number. This is the variable into which the function will copy the value of the task notification variable. The xTixToWait is a period of time in kernel time slices that we want to wait for the notification. Portmax delay is an infinite wait, meaning that the task remains blocked until a notification is received.
The notification is a practical method to share a small amount of data between tasks or from the interrupt handler.
If you want to send more than one 32-bit number between tasks, it's better to use the so-called queue.
In practice, it is a FIFO whose elements can be of any type, even a structure. The size of its elements must be specified when it is created, as well as the number of elements it should be able to store. CubeMX also provides a graphical interface for creating queues, which is shown in this figure. In the queue name field, you need to enter the name of the queue and a handle will be created to refer to the queue itself. In the queue size field, we need to specify the maximum number of elements. In the item size field, you can define the type of items in the FIFO. Here you can use your own types or structures. In the allocation field, you can choose between dynamic or static memory reservation, which was discussed earlier. You can place items in the queue with the xQSend function, which has 3 parameters. The xQ is the handle corresponding to the queue. The second is the PV item to queue. This is a pointer pointing to a variable which we want to place in the queue. Here, it is important to note that it is not the pointer that is stored in the queue, but a binary copy of the variable that the pointer points to. And at last, the xTick to wait is the waiting time given in kernel time slices. This has relevance only if other tasks are also sending data to the queue or if the FIFO is full. You can receive elements from the queue with the xQReceive function. This also has 3 parameters. The xQ is the handle identifying the queue. The PV buffer is a pointer that points to the variable in which we want to save received items. The xTicks to wait is the time we wait for data in case the FIFO is empty.
You can find the example program in the Lecture 22 Notify Solved folder, which shows you the use of the notifications and queues. We will not look at the source code in detail now, since you have all the information needed to understand the topic on your own.
We would like to draw your attention to a few small points. The program basically has 2 modes of operation. If you want to see how the queues work, you can comment out the define use notification line. If you want to use notifications, don't comment it out. If you want to use the queue, the Blinky task and button task threads send structures to the display task via this queue. The left side of the display is used to display the state of the buttons, and the right side is used to display the state of the LEDs. In the structure, we indicate whether it is a button or LED, what position the change occurred in, and whether a logic low or high change occurred. If you are using notifications, the program will work differently. Only the status of the buttons will be shown on the display. We use the notification variable of the display task, and we use its bits to represent the state of the buttons. Bit 0 represents button 1, bit 1 represents button 2, and so on. We encourage you to try this software yourself with both options.
In this chapter, we wanted to introduce you to the world of FreeRTOS. We hope you can use the knowledge you have gained through this example project.
By the way, FreeRTOS is very widespread, and it was the leading embedded operating system at the time the video was made. So you can find it often in real projects as well.
Thank you for joining us in this journey. In the next chapter, we will learn how to use the SD card. We will write and read files for which the use of recently discussed FreeRTOS will be essential. We hope you will join us there too. Goodbye.
Bye.